partial fraction decomposition. This algebraic technique allows us to break down complex rational functions into a sum of simpler fractions. In this lesson, we will define proper rational functions, perform decomposition with two distinct linear factors, and apply decomposition to solve complex integrals. This topic is a cornerstone of the IB Mathematics Analysis and Approaches higher-level syllabus. It is vital because it transforms difficult expressions into a form that is easy to integrate or expand using binomial series. You will frequently encounter this in Paper 1 and Paper 2, often as a preliminary step in a multi-part calculus question. Before we decompose a fraction, we must ensure it is a proper rational function. In the expression p of x over q of x, proper means the highest power of x in the numerator must be strictly less than the highest power in the denominator. For the higher-level syllabus, we focus on denominators that factor into two distinct linear terms. We use the triple bar identity symbol because this relationship must hold true for all values of x. Our goal is to find the specific constant values for a and b that make both sides of the equation perfectly equal. To decompose a fraction efficiently, follow these four systematic steps. Step 1. Factorize the denominator. Step 2. Set up the identity. Step 3. Clear the denominators. Step 4. Solve for constants a and b. In step 1, we ensure the denominator is expressed as a product of distinct linear factors. If it is a quadratic, factorize it first. In step 2, we equate our original fraction to the sum of two partial fractions with unknown constants a and b. Step 3 is the crucial algebraic move. Multiply the entire equation by the common denominator to create a linear identity. This removes all fractions, making the equation much easier to handle. Finally, in step 4, we find a and b. We usually use the substitution method, where we choose specific values of x that make one of the brackets equal to 0, allowing us to isolate and solve for the remaining constant. Let us apply this to a concrete problem. Express the fraction 5x minus 1 over x squared minus x minus 6 in partial fractions. Step 1. Factorize. First, we factorize the denominator. The quadratic x squared minus x minus 6 factors into x minus 3 and x plus 2. Step 2. Set up the identity. We equate the fraction to the sum of two parts with unknown constants a and b. Step 3. Clear denominators. We multiply through by the common denominator. Notice how the x minus 3 cancels for a, and the x plus 2 cancels for b. Step 4. Solve for a and b. To find a, we choose a value for x that eliminates b. Let x equal 3. Substituting 3 into the identity gives 14 equals 5a. Thus, a equals 14 over 5, or 2.8. To find b, let x equal negative 2 to eliminate a. Substituting negative 2 gives negative 11 equals negative 5b, so b equals 2.2. Finally, we state our result. 5x minus 1 over x squared minus x minus 6 is equal to 2.8 over x minus 3 plus 2.2 over x plus 2. This is our completed decomposition. We have successfully broken a complex fraction into two simpler parts. The most common reason the IB will ask you to perform partial fraction decomposition is to solve an integration problem. Let's look at how we would evaluate the integral of 5x minus 1 over x squared minus x minus 6 with respect to x. Integrating the left side directly is impossible with standard rules. However, using our previous result, we can rewrite the integral as two separate simpler terms. This allows us to use the natural logarithm rule for integration. The integral of 1 over ax plus b is 1 over a times the natural log of the absolute value of ax plus b plus c. Applying this to each term, we get 2.8 times the natural log of the absolute value of x minus 3, plus 2.2 times the natural log of the absolute value of x plus 2, plus c. By breaking the complex fraction down, we turn a high-difficulty calculus problem into a straightforward application of log rules. Always look for this strategy when you see a rational function inside an integral. Let's work through an authentic IB-style question. Find the values of a and b such that 7 over 2x squared plus 5x minus 3 is identical to a over 2x minus 1 plus b over x plus 3. Then, find the exact value of the integral of this function from 1 to 2. First, we check the denominator. 2x squared plus 5x minus 3 factorizes into 2x minus 1 and x plus 3. The identity provided in the question already gives us these factors. Multiply both sides by the common denominator to clear the fractions. To find a, let x equals 0.5 to 0 out the b term. This gives 7 equals 3.5 times a, so a must be 2. To find b, let x equal negative 3 to 0 out the a term. This results in 7 equals negative 7 times b, which means b is negative 1. Now we evaluate the integral from 1 to 2 of the decomposed fractions. The first term requires the chain rule in reverse. The integral of 2 over 2x minus 1 is 2 times 1/2 natural log of absolute value 2x minus 1, which simplifies to natural log of 2x minus 1. The second term is simply natural log of x plus 3. Substitute the limits. Upper limit 2 minus lower limit 1. Since natural log of 1 is 0, we are left with natural log of 3 minus natural log of 5 plus natural log of 4. Using log laws, this is the natural log of 3 times 4 over 5, which is 12 over 5. The exact value is natural log of 2.4. Even top students can lose marks on partial fractions due to simple oversights. Let's look at 3 common pitfalls. The most frequent error occurs during the calculus step. Students often forget to divide by the coefficient of x. Always remember that if the denominator is ax plus b, you must multiply the result by 1 over a. Students often try to decompose a fraction where the degree of the numerator is equal to or greater than the denominator. If you see an x squared over an x squared, you must perform polynomial long division before you can start the partial fraction process. When solving for b by substituting x equals negative 3, for example, students often miscalculate the resulting negative values. Double-check your signs, as a single minus error will lead to incorrect constants and an incorrect final integral. To maximize your marks in the IB examination, keep these 3 strategic tips in mind. Tip 1. Always explicitly write the line where you clear the denominators. Even if you make a calculation error later, this step earns you the method marks for showing you understand the decomposition structure. Tip 2. Use smart substitution. While you can solve for constants by equating coefficients, the substitution method is usually faster and less prone to error in a time-pressured exam. Choose values of x that make your factors 0 to isolate a and b immediately. Tip 3. Check for exact value requirements. IB questions often ask for an exact value when integration is involved. This means you must leave your answer in terms of natural logarithms or fractions. Do not provide a decimal approximation from your calculator unless specifically asked, or you will lose the final accuracy mark. Here is a key insight. Method marks are often awarded for the correct partial fraction form. Even if the constants a and b are wrong, never leave the page blank. Even if you are stuck on the algebra, set up the a over linear term plus b over linear term structure to secure early marks. It is time to test your understanding. Please pause the video and attempt these 3 questions. Easy. Express 1 over the product of x minus 1 and x plus 4 in partial fractions. Medium. Find the constants a and b such that x plus 7 over x squared minus x minus 2 is identically equal to a over x minus 2 plus b over x plus 1. Hard. Find the exact value of the integral from 2 to 3 of 2x plus 10 over x squared plus 2x minus 3 with respect to x. Take your time with the algebraic steps. I will provide the full solutions when you press play. Let's go through the solutions. For the first question, we set up the identity and clear the denominators. Let x equals 1, 1 equals 5a, so a equals 0.2. Let x equals -4, 1 equals -5b, so b equals -0.2. The final result for the easy question is 0.2 over x minus 1.2 over x plus 4. For the second, factorize the denominator into x minus 2 times x plus 1. Let x equals 2, 9 equals 3a, so a equals 3. Let x equals -1, 6 equals -3b, so b equals -2. So we get 3 over x minus 2 minus 2 over x plus 1. For the hard question, we factorize the denominator. Let x equals 112 equals 4b, so b equals 3. Let x equals -3, 4 equals -4a, so a equals -1. We now evaluate the integral from 2 to 3 of 3 over x minus 1 minus 1 over x plus 3 with respect to x. This integrates to 3 times the natural log of the absolute value of x minus 1 minus the natural log of the absolute value of x plus 3. Substituting the limits, we get 3ln2 minus ln6 minus the quantity 3ln1 minus ln5. Using log laws, this simplifies to ln8 minus ln6 plus ln5, which is natural log of 40 over 6. The exact value is the natural log of 20 over 3. To recap our session on partial fraction decomposition, keep these essential points in mind for your examinations. First, remember that decomposition is for proper rational functions, where the degree of the numerator is strictly less than the degree of the denominator. Second, the general form for two distinct linear factors is a over the first factor plus b over the second factor. Third, use the substitution method by choosing values of x that zero out the factors to solve for a and b efficiently. Fourth, when integrating partial fractions, always remember the rule. The integral of 1 over a x plus b dx equals 1 over a times the natural log of the absolute value of ax plus b. Finally, always provide exact logarithmic answers when requested by the question, rather than decimal approximations. Mastering these steps ensures you can handle complex integration and algebraic manipulation throughout the IB higher level syllabus.